The next topic is parallel models of linguistic planning. An alternative to the serial models advanced by Fromkin and Garrett are parallel models that assume that multiple levels of processing take place simultaneously during the course of language production. If you may recall, and we have just discussed the serial models, and those models proposed by Fromkin, Garrett, Levelt, and Delt, they advocated the models which take into account the series of stages which are involved in the speech production, and where we have seen that error occurring at one level do not affect other levels. But the alternative models, which are the parallel models, they believe that if error occur at one level, it may activate the processing at others or other levels that are also involved. So the difference is that in the serial model, one level is devoted to the distinct or distinctive processing of the speech production, where error happening at one level does not affect other levels, but here all the processes are simultaneously involved, and if error occurs at one level, it can and it may activate processing at other levels. So let's discuss now these parallel models of linguistic planning. Now, looking at these models, we see that Dell has different studies conducted in this area, and he assumes that there are 4 levels of nodes in permanent memory, and those nodes are semantic, syntactic, morphological, and phonological representations. They work in parallel. Separate representations of the intended message occur at each level, much as in the serial models. But unlike the serial models, however, these representations work in parallel. As a node at one level becomes activated, it may activate other nodes at the same level or at other levels. In terms of words, word over there is considered as a node in a network, and through that word, other similar or related words are triggered or activated. Now, consider the following example. For example, suppose a person activated the word reset at the syntactic level. This simply means that the person intended to place this noun in the syntactic frame being developed. Now, this activation at the syntactic level then triggers activation of the component morphemes RE and SET at the morphological level. So these morphological nodes further spread the activation to the phonological level as well. Activating the node for the phoneme R, an important assumption of the model is that positive feedback occurs from later to earlier stages of processing. Once a morphological node is activated, it may spread its activation to a syntactic node. For instance, once re is activated at the morphological level, it leads to the activation of other words with the re prefix, such as recell. Recell then spreads some of its activation to the morpheme cell and ultimately to the phoneme s. All of this activation decays exponentially over time so that eventually activation is reduced to 0. The parallel activation model explains this finding in terms of feedback from the phonological to the morphological nodes. True words have morphological nodes, but the non-words do not. As a consequence, errors favoring true words may occur by backward spreading, but this will not occur for non-words. This difference, according to Dell, is responsible for the lexical bias effect. Another important aspect is to see the phonemic syllablarity effect, the tendency for intruding phonemes to be phonemically similar in their distinctive feature composition to the target phonemes, where each phoneme that is activated spreads its activation to the corresponding set of distinctive features. In turn, the features then activate a number of phonemes that share one or more of these features. This increases the probability that an intrusion will be phonological similar to the target. Thus, parallel models assume that linguistic message is organized at semantic, syntactic, morphological, and phonological levels. Activation of nod at one level may trigger activation of nods at other levels.